In this section, we're going to start discussing lines and planes in three-dimensional space. The goal is to find different ways to describe lines and planes in R3 so that when we start doing calculus, we can quickly come up with the equation or the forms for lines and planes. Much like in two-dimensional space, we can easily come up with equations of lines if, for example, we know 2 points on that line. You know, in that case, it's natural for you to find the slope between the 2 points and then to use one of the forms of the equation of a line to come up with an equation. And then once we have that equation, we can use it. And that's our goal here, except we want to look at lines and planes in 3 space. In order to do this, we're going to need to use the vector notation and operations that we've done previously. All right, so we're going to start with lines. If we start in three-dimensional space, so I'll draw my x, y, and z axis here. There's x, y, and z. And let's say we have a line in three-dimensional space. I'm going to draw this line in red. So let's say I have this line here. And again, it looks kind of like it intersects the z-axis, but it could, but it doesn't have to. Right? So if I want to try to describe every point on this line with vectors, then I can do so in the following way. What I need to do is I need to pick a point on this line. And so I'm going to pick this point right here, and I'm going to call that point, just give that coordinates, x0, y0, z0. Now I'm going to look at a vector that's going to go from the origin to that point on the line that I picked. And I'm going to call that r sub 0, and that's a vector. So this is called a position vector because the vector is actually giving the position of this point x0, y0, z0. Now, once I have a point on the line and I have a vector there, notice that I can find every point on the line from that given point by looking at some vector that goes in the same direction as the line. So for example, if I have this vector here, and I'm trying to not draw it right on top of the red line, or on top of the red vector, but really that's where it should be. And if I call this vector v, every single point on the red line is obtained by taking some scalar multiple of v. For example, if it's the point that's at the tip of v, then it's just taking 1 times v. If it's a point over here, maybe taking 2 times v. And every point in between the endpoint of v and the point 2v over there is some multiple of v between 1 and 2. And so on, you could keep continuing out, and you could hit everything on that line to the right of the terminal point of r0 by taking positive multiples of r, and you can hit everything on the left side of x0, y0, z0 by taking negative values of v, negative multiples of v. Okay? And so this allows us to write down a couple different versions of a line in space. So we're going to define a couple forms for a line. So the first one is going to be called the vector form. So the vector form for a line L, and it needs to contain a point. Right, so we had in the previous picture, we had that point as x0, y0, z0. So I'm going to use that again. So it has to contain this point. And it's going to be parallel to a direction vector. Which we'll call v. And it'll have components, let's say A, B, and C. So this is exactly what I had in the picture that we just drew. we had a point on the line, x naught, y naught, z naught, and we had a direction vector v. I didn't label the a, b, and c, but it is a vector in R3, and it's parallel to that line. They pointed in the same direction. And so when we have this, the vector form is given by r of t, where r is a vector, and it's going to be r naught, which is my position vector from my initial point that I had, plus t times vector v. And t here will be a parameter. So this will be, if we write out the vectors, this is x naught, y naught, z naught, plus t times the vector abc. Right, so if we combine all of this, we get x naught plus ta, x1 or y naught plus tb, and z naught plus tc. Right? And here we want all possible multiples of that vector v, and so we want to take t as a parameter that ranges from negative infinity to infinity. Right? So this is one version of the form. It's the vector form, and it's called the vector form because it gives the line as a vector. It describes every point as a vector where that t is this parameter that ranges over all real numbers. Another form that's sometimes useful is the parametric form. If the vector form writes it as a vector, the parametric form should write it as a set of parametric equations. So the parametric form of L is the set of parametric equations that I'm about to write down, and they're actually already written on the screen. They're the components of the vector form of the line. So we have x equals x naught plus ta, y equals y naught plus tb, and z equals z naught plus tc. And again, t is going to range from negative infinity to positive infinity. So we again hit all real numbers in this description. Okay, so let's use these forms and let's look at an example. Right, so let's say we wanted to find the line that passes through the points P, which will be 4, 2, negative 1, and Q, which will be 1, 2, 3. So in order to come up with the equation of a line, we need two things. We need one point on the line. Well, in this case, we have two. And so we have a choice. For our position vector r naught, we can choose this to have the same components as the coordinates of P or as Q. And I'm going to go ahead and do it as P, because it really doesn't matter. It's just going to make a difference in what our answer looks like. Right, so our position vector here will be 4, 2, negative 1. And I need a direction vector, which we called V. And when we have 2 points on a line, like in this case, the direction vector is simply the direction from one of those points to the other. So I'm going to use the vector from P to Q. You could also use the vector from Q to P. Right, and so the vector from P to Q is going to be 1 minus 4, which is negative 3, 2 minus 2, which is 0, and 3 minus negative 1, which is 4. So we get negative 3, 0, 4. Okay. And so if we want to find the forms of a line, then if we want vector form, right, we know what this is going to be. We know this is going to be r naught plus t times v, where r naught and v are the vectors we just wrote down. So we can write down what this would be. This is going to be 4 minus 3t, 2 with no value of t because it's 0 times t, and negative 1 plus 4t. Right? And t here will range from negative infinity to positive infinity, so all real numbers. Right, so there's the vector form of our line. Right? If we wanted parametric form, we just write this as a set of parametric equations. So x has got to be 4 minus 3t, y is 2, and z is negative 1 plus 4t. And again, t ranges over all real numbers. Okay. So here are both versions of both forms of the line. As you can see, if you know one, the other one's pretty easy to do. But the thing with this to kind of point out is these are not unique answers. I actually made two choices when I made this function. I had two choices in this case for a position vector. I used point P. You could have certainly used point Q. I also had two choices for vector V, the direction vector. I chose the direction from P to Q. You could also choose the direction from Q to P, and it would change around the negative signs in this final version of the line. So these choices, while you can come up with these different versions, it is important to kind of realize that we could all come up with different vector forms for a line and both be correct. It's similar to how we use point slope form in high school algebra. You could choose different points and have a completely different looking point slope form. But if we would put it in the same kind of form, some kind of a slope intercept form equivalent, which we don't really have in 3 dimensions, if we were able to do that, then we would see that we do have the exact same line. And so let's look at another example. In this example, we're going to be given a line and asked to do something with it. So the thing we're going to be asked to do is to determine where this line, I'm going to give it in vector form. So this line has components 3 minus 4t, 2 minus t, and negative 1 plus 4t. So I want to know where this line intersects the YZ plane. Right, so we want to know when this intersection of this line and this plane occurs. So the only thing we really need to know here is that the YZ plane consists of all points where x is 0. Okay. And we know we want x to be 0, and so in the vector form of this line, we know that x is given by the parametrized equation or parameterized expression 3 minus 4t. So in order to figure out where this occurs, we need to find the value of t, where 3 minus 4t is equal to 0. All right, we want that first coordinate of the point on the line to be equal to 0 to be on the YZ plane. All right, and so this means we need 3 equals 4t, and therefore t to be 3/4. Right? And so this is the value of the parameter when we have the point that we want. And so to find the point on the line, we need to compute r of 3/4 and find what point we have. Right? So we know the x coordinate is going to be 0. I'm not even going to plug 3/4 into that expression. We literally set that equal to 0 and solve to get that t. For the second coordinate, I'm going to have 2 minus 3/4. And for the third, I'm going to have negative 1 plus 4 times 3/4. Right, so this becomes 0, 5/4, and 2. Right, so the point of intersection between the line and this plane is the point 0, 5/4, 2. So if you'd like to try something like this on your own really quickly, what shouldn't take a lot of time, try doing the same problem with the same line, but try looking at where it intersects the XZ plane and the XY plane. Right? And if you do this correctly, you should get the points -5, 0, 7, and 2, 7/4, and 0. Right? At least if I did them correctly and you do them correctly, then this is what you should get. But it's done very similarly, just using the different coordinates. And so we want to do one more example of a line, or involving lines. We've seen how to find the form of a line. We've seen how to intersect a line with certain planes, and we will come back to that something more general than the coordinate planes in a moment, once we know how to describe planes in 3-space. But the last thing we can do with lines is we can determine a point of intersection of two lines. Right, so that's what we're going to do in this example. So we want to determine the point of intersection of the following two lines. So the first line is r of t, and in vector form it's given by 2 plus 3t, -1 minus t, and 2t. And the other line we're going to give a different name to. We're going to call it q instead of r, and I'm going to use a different parameter. I'm going to use s instead of t. So it's going to be given by the vector form 7 plus 2s, -3 minus s, and 1 minus s. Right? So this line is the exact same idea, except we're using s instead of t. Right? So the key to thinking about this kind of a problem where we want a point of intersection is that we want the two x components of the vector to be equal. We want the two y components of the vector to be equal. And we want the z components of the vectors to be equal. That's the only way to have a point on both lines, is to have some point, a, b, c, where a satisfies both of those first components, b satisfies both of the second, and c satisfies both of the third. And so what we need is we must have values of s and t with the following three things holding. We need 2 plus 3t equal to 7 plus 2s. We need -1 minus t to equal -3 minus s. And we need 2t to equal 1 minus s. Right? And so we need all three of these equations to be true for some value of s and t. Right? And of course, there's only going to be one set that works if we have a point of intersection, because we can't have two lines intersecting more than once. Right? And so we can solve this system of equations in a couple different ways. But one possible way that we could look at this is if we first focus on the first two equations. I notice if I take the second equation and I multiply it by 3, right, then we're going to get -3 minus 3t, and that's going to equal -9 minus 3s. And I'm going to do nothing to the first equation. I'm just going to copy it over to the side. right? So I have 2 plus 3t equals 7 plus 2s, and negative 3 minus 3t equals negative 9 minus 3s. I can then add these equations together, and this will eliminate the variable t, which is which will help us solve for s. So when I add these together, we get on the right side, on the left side, we get 2 plus negative 3, so that's just negative 1. The t and 3t cancel out, and so we get 7 minus 9, which is negative 2. 2s minus 3s is minus s. And so when we solve this equation, we see that s has to be negative 1. Right? So we don't really have a choice here. If there's a point of intersection, then the parameter s would have to be negative 1 at that point. Right? Well, once we know that s is negative 1, then we can come back to, we use the first two equations here. I can come back to the third equation with this value. And so we want 2t to equal 1 minus negative 1, right, which of course is 2. And so 2t is 2, which means t is 1. Right? So we use the first two equations to find the value of s. We use the third equation to find the value of t. And then we can go and check, because there's three equations here, we can go back and check to make sure that this value of s and t that we found, s being negative 1 and t equal 1, work in all three of the equations. In this case, that is the case. And so in order to find this point of intersection, what we need to do is just find a point on either line, since the point's on both, where they have these appropriate values. So, for example, if I want to use the t value, we can use r of 1 as our intersection point. And when I substitute 1 in for t, we get 2 plus 3, which is 5. I get negative 1 minus 1, which is negative 2. And I get 2 times 1, which is 2. All right, so r of 1 is the vector 5, negative 2, 2. And so our intersection point is the point 5, negative 2, 2. Now, if you substituted s equal negative 1 into the equation, or into the function q, the vector function q, then you would also get this same point, right? Which makes sense because that's the point on both lines. Now, I will mention it is important here to double check that these points do satisfy all three equations, because it is possible to come up with two lines like this that do not intersect. If you follow the kind of procedure we set up here, you will get values of s and t, but they'll only satisfy two of the equations. They won't satisfy the third.